Hello. Today we're going to be talking about rational function transformations. Okay. I want to give you a quick video explaining transformations and some examples to show you how they work. But it's very similar to what we've been talking about, at least in the last several units, in terms of transformations. So let's get to it. This is what we know. Okay. So far we discussed transformations as absolute value functions, the V, quadratic functions, the U, and then cubic functions, right? Or really any polynomials. The more like curvy S-looking one, okay? We're now going to be talking in a very similar format using A, H, and K. We're going to be using it for rational functions. So let's talk about the parent function. What does it look like, and how do these three letters, A, H, and K, behave for this function? So this is the parent function of a rational function, okay? So we have 1 over x. We spoke about this function already, so you can tell that the asymptote, there's a horizontal asymptote here on the x-axis and a vertical asymptote on the y-axis. And those are the two things that really define this function the most, right? What is the horizontal boundary and what is the vertical boundary or limits to this function? Now, this parent function, we're going to be manipulating it, and we're going to be using this one instead. Let me make this a little bit bigger. So we're going to use A over x minus h plus k. Now, if you notice, if we put them side by side and we compare these two functions, right, notice how here in this first one, we have a 1 over x, and there's really nothing associated with it. But if we were to put an h and k next to it, this would technically be written something like this. F of x equals 1 over x minus 0 plus 0, which is why, if you look at this h and k, we have a horizontal and a vertical asymptote at the x-axis and the y-axis at zeros, right? Now, the h, and we'll talk about these in a little bit, the h will represent the horizontal shift. So if we're talking about a horizontal shift, we're talking about the vertical asymptote. Okay, and since we're talking about for the k, we're dealing with a up and down shift, right? Like the other letters before, h inside the parentheses was always left and right. The k was always up and down, right? The k will move it up and down, which means it will move the horizontal asymptote. And I can't fit it here anymore. It's supposed to say horizontal asymptote in that spot. Okay, here I see I can make this better. So the horizontal asymptote will be with the k. That's what's going to control it, right? So if h moves it side to side and the k moves it up and down, a quick recap, the a value is what gives it a vertical stretch and a vertical compression. It's going to make it stretch, right, or compress. Now that does not move the vertical and horizontal asymptotes. That will just move the picture itself. That will make the graph, and we'll talk about this in a little bit, it'll make the graph come further away from the asymptotes or closer to the asymptotes, okay, depending on whether it's a stretch or compression, right? Pushing away from the asymptotes or pushing it closer. And that depends on the a, right? A, if it's between 0 and 1, a will be a compression, And if a is greater than 1, we're dealing with a stretch. Oh, if only if I could spell stretch. Anyway, so this is a quick review, right? We've used A, H, and K, where A gives you the stretch or the compression. It even also flips it upside down, right? So if A is negative, we're dealing with a reflection over the x-axis. So it flips over the x-axis. What does that mean? It means that this function that's then below will now be above, and the function that's above will now be below, right? It'll reflect it over the x-axis if A is negative. So let's get to a few examples. We'll manipulate one at a time. I'll show you how it's an example of horizontal shift, a vertical shift. I'll show you how A is affected, and then we'll do some examples where we put it all together. So here we're dealing with the horizontal shift. I'm going to be showing you the parent function to begin with, and then show you what the function is going to look like after the equation occurs. So we're comparing everything to f of x equals 1 over x, the parent function, right, where it's centered at the origin. Now the x minus 2, if we think back to the rules of vertical asymptotes, right, we set the denominator equal to 0, right? So you want to set the denominator equal to 0 and you solve for x. If we do that, this is what we have. Move the 2 over, x equals 2. It means that our vertical asymptote will be at 2. I'm going to do this in blue. So if we go down to 1, 2, now our vertical asymptote will go through here. The horizontal asymptote will remain the same, but now the function is going to be shifted over to the right, 2 units. Okay? So it's moving the function over to the right 2 units, not moving it up and down at all. And hopefully this makes it kind of a refresher, right? The x minus 2, it's always going to be moving the opposite. The x minus h part, inside the parentheses, it'll always be opposite. So if it says minus 2, it'll mean it'll move it 2 units to the right. If it says plus 2, it'll move it 2 units to the left. Let me see if I can make this graph a little bit thicker to make this easier to see. So our function is being transformed over to the right. Maybe that's easier to see how it's shifting over. Okay? Let's talk about the vertical shift. Now notice how here we're comparing this to our parent function, f of x equals 1 over x. Now we're looking at the plus 2. So if our general function is f of x, x minus h plus k, now this plus k is going to move the function up and down. Since it's positive, it's going to move it up. What is it that's being affected by moving it up? The horizontal asymptote. So now we're going to be looking at the horizontal asymptote moving up 2 units up. So this red dotted line that's on the x-axis is now moving up. So this graph right here is going to move up 2 units. Just like that. Now, obviously, if I could make this longer, I would. But hopefully you get the picture that this picture is moving up 2 units. Here we're going to talk about the vertical stretch, and then next we'll talk about a vertical compression. So the stretch is being compared to this general function. Again, f of x equals 1 over x. Notice how this 1, right, this a value is a 1, now it's a 4. Since a is bigger than 4, since a is greater than 1, we're going to be dealing with a stretch. So this we're comparing this 1 to this 4. Okay? Since this 4 value is bigger, we're going to make this a stretch. And what does that mean? It means that the values that we're looking at are going to actually be higher. So if we're looking at a number here at 1 as an example, it'll actually be pushed up higher. Instead of it being here on the line, it'll be pushed up higher. Any number that we get is going to be pushed up a little bit higher since we're multiplying it by a factor of 4. Therefore, when you're dealing with a vertical stretch, it's actually going to bring it the function. Oh, let me see if I can do this again. That'll bring the function further away from the vertical asymptotes. So it's going to push itself outward, away from the vertical asymptote, because it's going to be going as a higher number. Okay? And this, of course, is we're comparing it to the a value being greater than 1. Here we have an example where a is less than 1. Again, we're trying to compare everything to the parent function. So the parent function says f of x equals 1 over x. Notice how the 1 and the 1 stay the same, but technically over here we have 1/4. The 1/4 is what we're comparing it to the 1. So since a is now between 0 and 1, we're dealing with a compression. Okay, so we're dealing with a compression because we're dealing with a 1/4 compared to a 1. Therefore, what's going to happen is all the numbers are going to shrink a little bit. So if we have a number that's here, because we're taking 1/4 of the number's going to go below it. Anything that's going to be on the line is going to be graphed below it, making it smaller or shorter, right? It's going to compress the function. So my actual function, when it's compressed, is going to come closer. It's going to squeeze in closer to the asymptotes. Okay? Earlier we talked about a stretch. The stretch is going to pull it further out, making the numbers bigger. A compression is going to make it smaller and closer to the asymptotes. It's going to squeeze it in. It's going to compress it towards the asymptotes versus stretching it away from the asymptotes. So let's review a little bit, right? Now here, what I want to do is I want to compare all of these functions. I want to compare them to not just the parent function, but the general vertex equation form. We have a, here, let me move this over to the side, it'll be easier. I want to compare everything to this right here. So this x minus h plus k, how does this compare to this function? Right? Notice how a remains the same. So a equals 1, so we're not going to stretch it or compress it. The minus h is going to be a plus 3, and the plus k is a minus 4. So we are going to be moving the vertical and the horizontal asymptotes. Remember, it's always the opposite behavior. So if it says x plus 3, this is going to move it 3 units to the left. Make a note, 3 to the left. And then the minus 4 is going to move it 4 units down. Okay? That's what we're looking at doing. So I'm going to look at my horizontal asymptotes and my vertical asymptotes, and I'm going to redraw them where I want them to be. And I'll do this, of course, in the color blue so that it stands out from the rest. So if I'm moving it 3 units to the left, I'm going to move my vertical asymptote 2, 3 units. Now my vertical asymptote is over here on the negative side. And my horizontal asymptote, because we're moving it 4 units down, I'm going to move it down here. 1, 2, 3, 4. Clearly I did not plan this, because then you would have had a better picture for me. but I'm going to take this exact same picture and sort of draw it in this quadrants that I drew. So I have a curve on this side, and then I have another one right below it. And hopefully we can see that this curves downward following the asymptote. Okay, so the big thing here is that we're moving the vertical asymptote 3 units to the left and 4 units down. So vertical asymptotes to the left, horizontal asymptotes 4 units down, shifting the graph over here. So earlier it was centered at the origin, now it's centered down here at the bottom. And that's actually a good way to think about it, right? This h and k, this -3 and -4, because it's the opposite, -3, -4 tells you the intersection of the vertical and horizontal asymptote. That'll be like the center, the new origin, or the center of the graph. In this example, notice how we have x minus 1. It's going to move it 1 unit to the right. The minus 2 moves it 2 units down. And here we're talking about the asymptotes, right? So 1 unit to the right is the vertical, 2 units down is the horizontal, and then this 3, because it's greater than 1, it's going to be a what? Yes, it's going to be a stretch. So what we're looking at doing is in this stretch, we're looking at pushing it away from the vertical asymptotes. The compression is going to come closer to the asymptotes, like really, really close. The stretch is going to push it away. So let's draw these asymptotes and let's see how this looks. Hopefully it's better than my previous picture. So 1 unit to the right. So I have a vertical asymptote here. My horizontal asymptote, it's 2 units down. 1, 2. Okay? And now I can draw my picture. Now, because it's a stretch, I'm going to go really, really far away as much as I can from this graph. Just to make it sort of obvious that it's wider and further away from the asymptotes than the previous one. All right, the previous one, it was a little bit closer to the red dotted lines. Now I'm looking at it further away because it's a stretch. In this last example, let's do one more and we can call it a day. Okay, so here we have, let's identify our values that we're dealing with. So I know that it's going to be moving 3 units to the left because of this plus 3. It's always the opposite inside the parentheses. So plus 3 means 3 to the left. The minus 1 is 1 unit down for the horizontal asymptote. And then the A value. What's the A value here? The A value equals 1/2. Notice how we're dealing with a 1 and a 2 in the front. Now 1/2 means it's less than 1. If it's less than 1, we're dealing with a compression. Right? The stretch was further away from the asymptotes. The compression is going to get really close to the asymptotes. So let's draw this picture. So 3 units to the left. Let's start with the vertical asymptote. 1, 2, 3. I'm going to draw a dotted line down at -3. And then the horizontal asymptote is 1 unit down. And then it's a compression. So we're going to draw this line really close to the asymptote. Let's draw that again. Hopefully it's clear, right? Around the bell section here, you can see how it's a lot closer to the lines than over here. Here it's a bit more of a circular approach. Here it's more of a rectangular or cornered approach because it's a lot closer to this new origin that we identified, which is going to be at h and k, which is -3, -1. 1, 2, 3, down 1 unit. So you're looking at going closer to the asymptotes when it's a compression versus further away when it's a stretch. I hope this puts it all together and it helps you out. Please let me know if you have any questions. And as always, we'll calculate later.